This is problem 72 from chapter 4. If a bicyclist of mass 65 kilograms, including the bicycle, can coast down a 6.5 degree hill at a steady speed of 6 kilometers per hour because of air resistance, how much force must be applied to climb the hill at the same speed and the same air resistance? So I've drawn a little picture here. We are told that the mass, 65 kilograms. The angle of the hill, 6.5 degrees, and a steady speed of v 6 kilometers per hour. And it's good to convert this speed to SI standard international units. So really just multiplying this to make it into meters per second. So you can do in 1 hour, there's 6 minutes. In 1 minute, 60 seconds. And in 1 kilometer, 1,000 meters. So you can multiply that out to get an answer in meters per second. It's just good to keep in mind before you plug in the number into a final equation. And we're told that there is air resistance, and we want to know how much force she has to apply to climb the hill instead of just coasting down it. So coasting down it, we'll take that to mean that she's not accelerating. She's just going at a constant speed going down the hill. So drawing a free body diagram of forces acting on bicyclists, there's gravitational force. There's a normal force from the road, perpendicular to the road, going upward. And she's going downward, so the drag force will be in the opposite direction. That's what I'm calling the force of air resistance, the drag force, FD here. And she's not pedaling, she's just coasting, so she's not applying any force to go downward. And we can create our coordinate system so that two of the forces are along the axes. And we know that this angle here, this green line being the horizontal, and this blue line, the x-axis being along the road, which is at an angle. You can see that this is also theta, and this is a 90-degree angle. So is the corner here of these two blue lines of the system, so that this angle is also theta, because this will be 90 minus theta. So then to make up this square right here, but then this one also is 90. 90 minus theta means that this has to be theta. So we can just redraw this. So now X is pointed in the direction she's going down the hill. Just rotating that picture. This is angle theta. And we know that there's going to be a net force in the x direction, but it's actually 0 because she's just coasting. So no acceleration. And bringing her down the hill is the component of gravity. Just drawing a right angle here. In the x direction, the length is the magnitude of this vector, mg. And we need the sine of that angle to find this component here. So that component is mg times sine of theta. And in the opposite direction is the drag force. So we don't know what the drag force is. So we're calculating that first to be able to answer the question, which is how much force must be applied to climb up the hill at the same speed and within the same air resistance. So we aren't going to be able to figure that out until we have an idea of what the force of the air resistance is in terms of the given quantities. So then we can just solve for FD here. And we are given the mass, the angle theta, and g is a known constant, acceleration due to gravity. So now we know the drag force. And then we want to consider when she's pedaling up the hill. So now she's going upward. It's the same hill, same angle, same air resistance. So we still know that drag force. And now she also has to pedal upward. So I can draw a new free body diagram. She's still experiencing the force of gravity going straight down toward the center of the earth. Still a normal force perpendicular to the road acting on her. She's applying a force that's bringing her upward. I'll label F. This is what we want to find. And then the drag force, the force of air resistance, is opposing that motion. So this is the drag force opposite the force she's exerting. And again, we can draw a coordinate system. That should be along the same line. Maybe I'll try to. And we just show that this angle should be theta again. So everything's the same except we have the drag force in the opposite direction and an additional force that she's exerting, bringing her up the hill. So then we can just write an equation for the x direction. She's moving, so A, I don't know what A is, but I guess we're told that she's moving at the same speed, at a steady speed. So A is actually still 0. We want to know how much force she needs to exert to move at the same speed. So there's no change in that speed. So A is 0. And we have the drag force. We have this component of gravity. Cosine of theta. It might be easier if you tilted the axes to see it, but we're talking about this component down here. And those are in the same direction, FD and mg going downward, which I've labeled as positive. And then in the other direction is the force she's exerting. And maybe it'd be more intuitive since she's going upward to label x going upward as well. But we can solve for F. F is going to be this drag force plus mg times cosine of theta. And we can plug in drag force in terms of what we found just considering the case when she's coasting downhill, mg sine theta. So I'll factor out the mg of cosine theta plus or I think for the x direction, I made a mistake in writing down cosine theta because in the x direction we're still talking about opposite of that angle there in the diagram. So this is the sine theta again. So let me just sine of theta. So you have mg, this is theta. And so f is mg sine theta, so then we just have plugging in the equation for the drag force, we just have 2 mg sine theta. And we know the mass, we know theta, and g is a constant, so then we can answer this question and find the force just by plugging in the numbers now. $65 kilograms. And the angle is 6.5 degrees. So we never even had to use the velocity. We just had to know that it was constant to know that she's not accelerating this problem. And plugging in all those numbers, you should get 140 newtons.